Welcome everyone to the study guide review video for the 8th grade Unit 2 test. Let's just dive in. Question 1. Which statement is true? A. Dilations of a polygon keep side lengths the same. B. Dilations of a polygon multiply the angle measures by the scale factor. C. Dilations of a polygon must be similar to the original polygon. And D. Dilations of a triangle always make the sides shorter. Okay, this is a mild level question testing 2A, which is your understanding of dilations, that competency. Okay, so going through this one by one. Dilations of a polygon keep the side lengths the same. Normally, that's not true. Dilations of a polygon, the side lengths get multiplied by the scale factor. So if the scale factor is 1, that's true, but it's not always true. Get multiplied by the scale factor, so those side lengths can get bigger or smaller. Okay, that's like a key feature of dilations, changes the size. B, dilations of a polygon multiply the angle measures by the scale factor. Okay, that is also incorrect. The angle measures stay the same. So we've kind of swapped these. Angles stay the same. In order for, you're going to have a similar figure when you dilate a shape, same angle measures, same shape, different size. C, dilations of a polygon must be similar to the original polygon. That is true. Okay, dilations create similar figures. Dilations don't create congruent figures necessarily because they can change the size, but they do create similar figures, same shape, different size. And then lastly, we have D, dilations of a triangle always makes the side shorter. That's not true because it can also make them bigger. And if the scale factor is 1, which is technically a dilation, it can make them the same size as well. Cool. Okay, now going to a medium level question about dilations. We're supposed to actually dilate this triangle. So draw triangle A prime B C prime, which is a dilation of triangle ABC with center A, 0, 1. So here's going to be my center and a scale factor of 3. All right, so to dilate a shape, we're going to say what are the distances and directions from my center to my vertices. So to get from A to C, because A is my center, I go up 1, right 2. Okay, that's this move, up 1, right 2. So then if my scale factor is 3, I'm going to take that and I'm going to multiply by 3. So instead of going up 1, I'm going to go up 3, and instead of going right 2, I'm going to go right 6. So I'm multiplying by 3 there. Okay, and then I can do that. Up 1, 2, 3, right 1, 2, 3, 4, 5, 6. And this will be my new C prime. Okay, do the same thing from A, which is again my center, which is why I'm starting with A, to B. To get from A to B, I go right 2. So to get from A to B prime, I take that right 2 direction and I multiply by my scale factor of 3. So instead of going right 2, I go right 6. So that's going to take me here, and this is going to be my new B prime. And then, of course, I don't always write this, but A is my center. I still technically have to say, how do I get from my center to the last vertex, which is A? So basically, I go 0, and then I multiply by 3, and I get 0, right? So it doesn't change. So here is my dilated shape. Okay, good enough. A little messy. Yeah, I'll fix it. Okay, dilated triangle. And we should see it looks like the same shape as my original triangle, but it's just 3 times as large, and it's growing out of that point A, which is my center. Awesome. Okay, and finally, in this unit, in this competency, we have 2A, which is now like the hardest level question for dilations. So here we have polygon G is similar to polygon A. Describe a sequence of transformations that takes polygon A to polygon G. Include all necessary detail. Okay, so I'm starting here, and I need to get this mapped onto polygon A exactly. So first thing I'm going to need to do is I'm going to need to rotate it, okay, because I need it to be facing the same direction. So first, rotate polygon G. This is going to be 90 degrees counterclockwise around point T. Okay, so when describing a rotation, I'm going to need all that detail. I'm going to need the angle that I'm rotating, the direction I'm rotating, and the point that I'm rotating around. Okay, so I can see here, I just need to get it like a quarter turned around, right? It's like a 90-degree turn. A clock doesn't go this way. Okay, a clock goes the other way. So this is a counterclockwise rotation, and then I want this point T to stay where it is because that's in the right spot. Okay, so once I rotate it, then it's going to look like this. Okay, that would be like G prime after that. And you'll have access to tracing paper, of course, so that could be useful as well. Okay, now that I've done that, I should see that it's facing in the same direction, and one of the points is matched up, right? So this is where we want it to be. So now we just need to dilate, make it bigger, to map G prime onto A. So how many times bigger? Well, originally this is 1, and then the new thing, this is 4. So I need to go 4 times bigger. You could check that with any of the sides, but it needs to get 4 times larger. The side lengths need to go from 1 to 4. So we'll do that. Okay, and then we dilate the polygon with a scale factor of 4 and a center at T. Again, this T is my center because that's already in the spot where I want it to. Okay, that I want to keep it to stay still, and then I want the shape to get bigger and dilate from that point, and like kind of grow from that point. So there we go. Remember, you need all detail here to get full credit for this question. That's why it's a spicy level question. You need the degree, the direction, the center for the rotation, and the scale factor, and the center for the dilation. Okay, then we're moving on to the next competency that's we're being tested, which is on similar figures, similar polygons, similar triangles. So here we're supposed to circle all of the triangles that have to be similar to triangle T. So if I take a look at triangle T, I have this angle is 104 degrees. Here, this angle is 44 degrees. And then they don't tell us what that angle is, but we can find it because when we have 2 angles given to us in any triangle, we can always find the third because we know that there's 180 degrees in any triangle. Okay, the angles add up to 180. So again, 180 degrees total in any triangle. So to figure out this angle, I'm going to do 180 degrees minus 104 degrees minus 44 degrees. It's not really the right way to write it out. I'll do 104 plus 44 first, and that's 148. And then I'll subtract it from there, and we're going to get 32 degrees. So now I know that. And they also give you the side lengths, which honestly don't matter for this question. This question is really just testing our understanding of the angles. We can keep note of it, but as will be true on the test, the side lengths are really there just to mess you up a little bit. Okay, so all of the triangles that must be similar. So what we know is that when all the angles are the same in a triangle, that's enough to prove that the triangles are similar. So just write that, same angles in a triangle. It's not true for all the polygons. In a triangle means similar. Okay, so we just have to find which of these have the same angle measures. Okay, it has to be for all 3. So A is going to be wrong because we know that that's 104, which is good, but then we don't know what these are. So we have no reason to know that those are 32 and 44 degrees. Okay, so unless they tell us one of those, we can't figure it out. We don't know the angles are all the same. So it's possible it's similar, but it doesn't have to be. Okay, question B, or number B, B, we have this is 104 degrees. This is 32 degrees. And so then we can do the same thing. We can figure out what that is by doing 180 minus 104 minus 32. And we kind of already did that. That's going to, like, in a different way over here. This has to be 44 degrees, just like we had in this triangle, right? This was 44, this was 104, and this was 32. Because these three numbers add up to 180. So that also, these will add up to 180. So we have the same angle measures. All three of them are the same. So yes, okay, that is one of the right answers. Okay, same idea for C. We have the same angle measures are given. 104 is given, 44 is given, and then this has to be 32 degrees for the same reasons as was true in our original. So we have the same angles. All three angles are the same. So that's going to be similar. D, we are only given one angle measure, and it's not the same as the one in the original, so that's going to be wrong. The way they're trying to trick you here is they do tell you that these side lengths are the same, but yeah, the angle is different, so that doesn't really matter. And you can just look at these two triangles and see that they don't appear to be the same shape. And then E is going to be correct as well for the same reasons as before. This is 104, this is 32. So then if we subtract, that has to be 44 degrees. So all three of those triangles have the same angles as triangle T, so they're all going to be similar. They must be similar. Another medium level question for this, I'm testing our ideas of similarity. Circle all the polygons that are similar to polygon A. All right, so some key things we notice about polygon A. This, we have to do more about the side lengths, having equivalent ratios of the side lengths. So here I see this is 4, 4, 4, and then this triangle sort of has like a height of 2. Okay, if we want to break that up, so that's my original, and we're looking for triangles that, or polygons that appear to be the same shape. First of all, we can just eliminate D. We should be able to do that visually. D is too wide, right? It's too wide and short, so the proportions aren't right. That is 4, that's 2. So it should be that the height and the base are the same. We can do the same thing here. This is 4, but then this is 6. Okay, so for the like square part, or really like rectangular part, I guess. I mean, it's both. The height and width are the same. Right, 4 and 4. So if that's 4 and 2, that can't be it. And if this is E is 4 and 6, that can't be it, because that one, in that case, is too wide. Okay, and then we can check B, C, and D. I think all of these look right. This is 2, 2, 2. And then if I check this height, that is 1. So in that case, if I think about like what's the scale factor, that's taking A to B, a scale factor of 1/2 would do that. It's just half as small. You also, of course, would need to rotate it, but that doesn't matter when we're talking about similarity. They just need to, you can orient, you can do any sort of rigid transformation to it, and you can dilate it. If some scale factor will take us there and it's the same shape, then it's right. So that is correct. Okay, for C, C is the exact same size. This is congruent. 4, 4, 4, 2. Okay, that is also correct. I'm going to make a note about that. If shapes are congruent, they are also similar. Okay, so right, we often say that shapes that are similar are the same shape and different sizes, but it's not that they have to be a different size, it's just that they can be a different size. Okay, so congruent shapes, by definition, are similar. It's like a square is necessarily a rectangle, but a rectangle isn't necessarily a square. Congruent shapes are similar. Similar shapes aren't necessarily congruent. Okay, and then for this one, this is a height of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we got like 6, 6, and 6. And then here, this is a height of 3. So we have the same sort of ratios of these side lengths. To get from 4 to 6, we're multiplying by 1.5. So, and to get from 2 to 3, we multiply by 1.5. So that one is also correct. So for B, it's a scale factor of 0.5. For C, it's a scale factor of 1. And for F, it's a scale factor of 1.5. None of what I'm writing, like this isn't required writing, this is just my work. So all you have to do is circle it. But, that's just sort of the explanation. Cool. I now have a spicy level question for testing similarities of polygons and triangles. We have the triangle DEF and ABC are similar. Determine the exact lengths of the segments BC and AC. Okay, so for this, we know that when we have similar triangles, the quotients of the side lengths are equivalent. And this is connected to slope, which is why these are mixed together. It's an important concept for similar triangles. The quotient of side lengths, really of corresponding side lengths, ones that match up, are the same. Okay, the quotients are going to be the same, so we can sort of get like a scale factor relationship. So like from here, this is 3 and this is 6. Okay, I'm like, okay, that's from 3 to 6. So how do I get from 3 to 6? What's the scale factor I'm multiplying by? I'm multiplying by 2. So then I can do the same thing here. There needs to be the same ratio. So the longest side has to be 2 times as big as this side, AB or DE. So 4.8 times 2 is going to be 9.6. So I know that. And then I do the same thing here to get from D to E. 3 divided by 2 is 1.5. Or 3 times 1/2 is 1.5. So if you don't know that in your head, you can do 1.5 divided by 3, right? So you're saying like 3 times what equals 1.5, not 1/5, 1.5. To do that, you can do 1.5 divided by 3, and you're going to get 1/2, or 0.5. So you can do it with that either way, or multiplying by 1/2 and dividing by 2 are equivalent. So here, I'm going to either do 4.8 and divide by 2, or multiply by 0.5, and that's going to be 2.4. Ultimately, you need to have the same ratio of the side lengths, or the same quotient of the side lengths when you divide them. Cool. All right, now we've moved on to competency 2C, which is slope. Plot the points 4, 0, and 10, 3, and draw a line that passes through both points. What's the slope of that line? Okay, so I have the point 4, 0 is right here. 10, 3 is right here. Going to draw a line, not a line segment. So I'm going to have arrows on both sides that passes through both points. And then to find the slope of the line, I'm going to create a slope triangle. And slope is equal to the vertical change between the 2 points divided by the horizontal change. We could also think of it as like the height of the right triangle that you create divided by the base. People also say the rise over the run. There's lots of ways of saying it. But the height of the triangle here is 3. The base is 6. So that's my slope. 3, 6, which simplifies to 1/2, which is 0.5 as a decimal. In general, the best version of this slope is 1/2. People like slope is much more helpful when it's in fraction form, as we'll continue to see, versus decimal form. But ultimately, I would accept any of those on the test. Cool. All right, last question, although it has 4 parts, and definitely the most challenging is question 8. So we have 2 triangles. The 2 triangles on line N are similar. What's the slope of line N? Okay, so this is a basic slope question, the mild question for slope. To find the slope of the line, you pick any 2 points that are on the line, you create the slope triangle, right? And then we do this same thing. Slope is either vertical distance between the points divided by the horizontal distance, or it's like the height of the slope triangle divided by the base. And here my height is 2.5, my base is 2. So we just do 2.5 divided by 2, and that is 1.25 or 5/4. Okay, again, either of those are right. You would probably do 1.25, which I would accept, but it is helpful to write slopes as fractions. So that's also 5/4 is probably better. Cool. Okay, so that we just have to divide the height divided by the base, and we can find the slope of the line. So again, that's describing. Slope is about the steepness. That describes how steep this section is, and then that's because it's a line, it's also saying how steep this is, and this is, and this is. Okay, so then what does that mean? So what is the value of y divided by x then? So again here, this is trying to bring all these ideas together conceptually. These are similar triangles. If they're similar, then that means that the quotient of the corresponding side lengths are equal or are the same. So these are similar triangles. Y divided by x then has to be equal to 1.25 because it is equal to like the corresponding side of 2.5 divided by 2. So it's the same because we're ultimately y divided by x would give me the slope of this line. 2.5 divided by 2 gives me the slope of the line. When we have similar triangles, you can divide the side lengths that match up and you'll get the same number. So it doesn't matter if you don't have to know these, y and x. You don't have to know those. If you know these, you know that whatever you get when you do y divided by x is going to be equal to this. Same ratio, or same quotient. I mean, those are saying the same thing. Okay. C, describe the sequence of transformations that proves triangle ABC is similar to triangle CDE. You're not able to provide all detail, but explain in as much detail as you can. Okay, so these are similar. They told us that, but now we want to explain why that's true. So again, this question is trying to bring all the 3 different competencies together. To get from ABC, right, this is my original, and I want to get it here and prove that those are similar. Okay, I'm describing how can I move one to the other by translating, rotating, reflecting, and or dilating. Okay, so first thing I would want to do is I'd want to translate. I'd want to slide the shape over. There are lots of ways of doing that, where you want to pick it, so it is sort of open in that way, but I know my inclination, I think, is to move it like that. So I'm going to take, translate it up and to the right so that A maps onto C. Okay, but you could also translate it so that C maps onto E or that B maps onto D. All of those, there's a version that works. But I'll just describe this way. So translate ABC up and right so that A maps onto C. Okay, now I'm not providing all the detail I normally want to provide when I'm translating because I don't know how many units up and how many units right. So that's what this "you can't provide all detail" is referring to. But it is like a clear picture of what's happening. So again, I'm taking this, I'm translating it up, and then what I need to do, then I would need to shrink it, dilate it, and I need to have a center of point C, because that's the point that's already in the right spot, and I want to keep where it is. It looks like, from the picture, it's about a scale factor of 1/2, but we don't know that for sure. So we're just going to say dilate it with a center of C, so that it maps onto it. Okay, so since we can translate and dilate to take from one to the other, then we know that that these two are similar. Okay, so that's proving that it's similar. And then the last one, explain why this picture shows that the slope of a line is the same between any 2 points on that line. Okay, so to reiterate the question, if we have any line, we have this line N, we can find the slope of line N, just like we can for any line, by picking any 2 points that are on that line, creating a slope triangle, and taking the vertical distance divided by the horizontal distance. It doesn't matter which 2 points we pick. So why is that true? Why does it not matter which 2 points we pick? It doesn't matter because all the triangles that you're going to create by doing that will be similar to each other. And in similar triangles, the quotient of the corresponding side lengths are equal. So when you take the vertical divided by the horizontal, or the height divided by the base, you're going to get the same thing no matter what, right? And that's sort of like what this y divided by x is saying. We don't know what those are, but we do know that no matter what, you're going to get 1.25 when you divide them. Okay, so that's the answer. I'm going to put in words. So slope triangles formed on the same line will all be similar to each other. Okay, that is huge, that the slope triangles are similar. So no matter what 2 points we pick on this line to find the slope and to form these right triangles, all of those triangles will be similar to each other. And thus, we know that the quotients of similar triangles are equal. So since those quotients for the side lengths of similar triangles are equal, when we then find the slope and we do the height divided by the base, or in this case, y divided by x, right, which is representing the height divided by the base, you're going to get the same number, which will be your slope, regardless of the 2 points that you pick to form your slope triangle. Okay, so the key idea is since the triangles are similar, then the quotient of the corresponding side lengths are the same. So it doesn't matter which points you pick, the slope will be the same. Cool. All right. Good job, everyone. Good luck.